Greetings, everyone. In this short video, what we're going to see is an interesting thing I learned from Paul Lockhart's new book called The Measurement. You might recognize him as the author of A Mathematician's Lament. It's a must-read for any teacher of mathematics. What was interesting for me is apparently a piece of Babylonian mathematics is that every product you can think of here described as A times B, representing the area of this rectangle. Every product is writable as a difference of squares. If you think about it, this might make sense to you, but it wasn't obvious to me until I thought about it. Then I had an aha, of course, moment. But what we're going to do is we're going to see how is it possible to start with a rectangle like this with dimensions A and B, and its area is given by the product A times B. And we're going to learn how is it possible to convert it to difference of squares. Here you see a big square and then a small square removed from it. So difference of squares is the remaining red area here. So we're going to learn that this A times B is equal to this difference of squares area here. What I would like to show first of all is a procedure here. So let me just quickly explain what we're going to do. We're going to start with the rectangle here, and what we're going to do is we're going to understand how to truncate this rectangle and add a piece so that it represents a difference of squares. So let me just walk you through this process. Imagine you start with this rectangle, and we'll discover in a few minutes what this truncation amount has to be. But imagine that you could cut this green area here in such a manner, and let me just actually explain to you how this is done. Imagine we take this and we rotate this by 90 degrees like that, and then imagine now we take it and slide it across to here. You're going to end up with a shape like this. It can be shown that this for this difference of squares to work, the remaining piece here has to be of length A plus B over 2, the average of the A and B values. And then this distance here has to be the half of the difference of the A and B values. Okay? So when you add this green piece, take it from here and put it here, you're going to end up with a pattern here which shows you clearly that if you have a big square and remove the smaller square, you're going to get basically what is called the difference of squares. The area is equal to the product of A and B. Let me just show you this other step one more time. So we're going to take this green area, we're going to truncate the original rectangle by rotating it 90 degrees and appending this piece now to this side. We're going to create this gap here, which is itself a square. Now you might wonder, how is it possible to do that? So here is a simple, hopefully not too complicated, algebraic explanation why it works. It turns out that this difference of squares is created by A plus B over 2 and A minus B over 2 squares, difference of these two squares. So let's actually do a little proof of this. So imagine I have a product AB, and I am told that I have to show that it equals to a difference of squares, x squared minus y squared, for some x and y values that I'm trying to find out. Now the beautiful thing about difference of squares is that they factor beautifully into x plus y and x minus y. And for some of you at this point, you immediately see, oh, of course, every product is a difference of squares because difference of squares can be written as a product. But to continue a little bit further, so that means that x plus y value here has to equal to a, which I'm taking in our geometric example as the longer side. And then x minus y has to be this shorter side b. When you do some algebra, add these two expressions, you get 2x equal to a plus b. And when you subtract these two expressions, you get 2y equals a minus b, which immediately leads to the fact that x has to be the average of A and B, A plus B over 2, and Y has to be half the difference of A and B. It's kind of beautiful, actually, and it is sort of surprising to me that this was not automatically obvious to me. You may want to see an example. If you take two numbers like 15 and 13, their average is 28, over 2 is 14. When you square that, you get 196. Half their difference is 15 minus 3 over 2 is 1. Square that, you get 1. No wonder 195 is equal to 196 minus 1. Okay, it'll be fun to actually explore this on your own, but I just want to show you that when you change the dimensions, and let me actually show you right here, it might be easier to see. When I change the dimensions A and B, observe, let me actually pull this back to here. Observe that the shape sort of will automatically adjust itself, and it might be easier to actually see here. And observe that you still have two squares difference creating the original area. So you could dynamically play with the A and B parameters and understand how it leads to the difference of squares always equaling to that product. Okay, I hope this was some food for thought, and I hope you enjoyed it. I strongly recommend reading Paul Lockhart's books. They're quite mind-opening and really teaches you mathematics from the gut level. Alrighty, take care.